Hi, I am Nasir Ahmad, Assistant Professor of Physics, Government College Forum and Chintamani. Today we will be discussing about BSc Physics, paper 503 under the heading Astrophysics, Solid State Physics and Semiconductor Physics. And the contents of these videos are Fermi Dirac distribution function and Fermi energy. So what is Fermi Dirac distribution function? According to Fermi Dirac distribution function, all the particles in the system are indistinguishable and they obey Pauli's exclusion principle. So what we mean by that is that not more than two electrons can occupy the same energy state or level on filling the particles in the energy levels. So according to Fermi Dirac distribution function, the probability f of e that a given state with energy E is occupied with electrons at a steady temperature T is given by f of e is equal to 1 by e power e minus ef by kt plus 1, where f of e is the probability of finding an electron in a given energy state whose energy is E and ef is the Fermi energy and k is the Boltzmann constant and T is the absolute temperature. Now there are three different cases here. In the first case we see what will the probability of occupation for the energy states below EF at absolute 0. In that case, f of e is equal to 1 by e to the power minus infinity plus 1, and you get this as e power minus infinity by substituting in the last slide. In place of t we have to put 0 Kelvin, and in place of e we have to put e less than ef, so that we get e to the power minus infinity, and e power minus infinity is 0, so we get it as equal to 1. So the probability of finding an electron in an energy state below Fermi energy is always 100% or equal to 1. So this means that all the states below the Fermi energy level are occupied by electrons. Next, what is the probability of finding an electron in an energy state whose energy is greater than the Fermi energy at absolute 0? In that case also, by substituting t is equal to 0 and e greater than ef in the expression for Fermi Dirac distribution in slide number 2, we get f of e is equal to 1 by e to the power plus infinity plus 1, and e to the power plus infinity is infinity, so 1 by infinity is 0. So this result tells us that all the states above the Fermi energy level are unoccupied. The third case is what happens to the probability of occupation at temperatures greater than 0 Kelvin, which we call as the ordinary temperatures. So at ordinary temperatures we see that though the value of the probability remains 1 for E less than EF, that is for energy states just below the Fermi energy level, it starts reducing from 1 for the values of E close to but less than EF, as I told earlier, and this can be seen in the figure. The value of f of e becomes half at e is equal to ef. This is because at e is equal to ef, f of e is given by 1 by e to the power ef minus ef by kt plus 1, so that the value of the exponential term is 1, because we get e power 0 here, and e power 0 is 1 plus 1 in the denominator. So this is equal to 1 by 2. This means that there is a 50% probability of finding an electron in an energy state or level whose energy is equal to Fermi energy level at ordinary temperatures, that is at temperatures greater than 0 Kelvin. Further, for energy levels greater than Fermi energy level, the probability value falls off to 0 very rapidly. Hence, the Fermi energy is the most probable, or the average energy of the electrons across which the energy transitions occur at temperatures above 0 degree absolute. The dependence of the Fermi factor on the temperature and energy is shown in the figure. So here we are plotting f of e along the y-axis, energy along the x-axis, and the plot of f of e versus e is shown in two cases here. The first case is when the temperature is equal to 0 Kelvin. In that case we get a rectangle here, which tells us that all the states below EF are filled because their probability is equal to 1, and the energy states above EF are empty because their probability becomes 0 at EF. And for temperatures greater than 0 Kelvin, you can see that for E less than EF, very close to EF, the value of f of E starts decreasing, and the value of f of E is equal to 0.5 or 50% at E is equal to EF for temperatures greater than 0 Kelvin, and for E greater than EF, the value of f of E falls off very quickly to 0 above EF. Now what is Fermi level? The highest energy level that can be occupied by electrons at 0 Kelvin is called as the Fermi level. Also, at 0 Kelvin, when the metal is not under the influence of any external electric field, all the levels above the Fermi level are empty and those below the Fermi level are filled. Now, Fermi energy is the energy state at which the probability of occupation is 50% at temperatures above 0 Kelvin. So here in this diagram you can see that all the energy states up to Fermi energy level are filled. So highest filled energy state is called as the Fermi energy level, and all the states above Fermi energy level are empty at 0 Kelvin. Thank you.